Yes.
Powers.
Does that mean I can walk around a little?
All right, we're gonna get started.
That's right. So if you lace it,
Sorry?
There's more outside. Okay.
All right, so we're going to start this session on magnetic fields with our first talk by Irina Butsky on magnetic field phase structure in the neutral ISM.
Hello, thank you for the introduction. I'm very excited to be here and to talk to you all about some of my recent research. And probably for the first time in like 10 years, I'm not going to be talking about cosmic rays. So instead, I'm going to talk about our interstellar magnetic fields. And so I thought I would take the opportunity to start with this gorgeous image, which I'm sure all of you have seen before, but I doubt anyone will mind seeing it again, that traces the structure of the magnetic field in the Milky Way. And kind of right off the bat, you'll probably notice that this isn't an image of the actual magnetic field. Really, this is an image of polarized light coming from dust that just traces the outline of the magnetic field. Another way in which we can kind of infer the structure of the magnetic field is by looking at H1 emission, like this beautiful image from the GALFA H1 survey showing neutral hydrogen emission colored by different velocity channels. And what you'll see is there's some mixture of more diffuse emission as well, or that's punctuated by more dense, like filamentary structure. And Susan Clark, who's my faculty sponsor at Stanford, has really done a lot of work showing that this filamentary structure is actually aligned with the magnetic field in the interstellar medium. Now, my background is in theory and computation, where we've been just spoiled by having this three-dimensional information of our simulated galaxy or magnetic field basically at any point in time and space. And so from that, we know that galactic magnetic fields are quite tangled, and they vary in their strength and their topology, both spatially over time and with different gas phase. And so the challenge is then, even though we have this incredible data, it's inherently a 2D projection of the true three-dimensional magnetic field. And so what I've been kind of really interested in lately is thinking about how do we know, or how do we infer this 3D structure of the magnetic field from 2D observations. And so this is, important for understanding how the galactic magnetic field, affects ISM structure. It's important if you want to understand, say, how cosmic rays propagate throughout the galaxy and how that changes with gas phase, which actually has a lot of implications for how those cosmic rays couple to the thermal gas in the galaxy. But also, if you don't care about galactic magnetic fields at all, you still need to understand them if you want to do things like, say, test your theories of cosmology, and if you want to measure, say, the polarization signal from the CMB, you first have to subtract out the galactic contribution. And so we really want to understand how the magnetic field changes in different gas phases along our line of sight. And so this is something that Susan's group has been working on a lot lately, and there's this awesome recent paper by Minji Lee, who's a grad student in Susan's group, that pointed out this positive correlation between the polarization fraction, kind of like in that first image we showed, and the mass fraction of the cold neutral medium in the H1 emission. And so what this plot is highlighting is the Spearman correlation on the y-axis between the polarization fraction and the FCNM, the mass fraction of CNM in blue, and the total hydrogen column density in orange. And so you see is, even though there's no correlation between the polarization fraction and the total gas column density, there clearly is a positive correlation between the polarization fraction and the cold CNF, or the cold neutral medium column. And so using that observation and doing a lot of analysis I'm going to skip over, they came up with this picture of the ISM where the cold gas has a more ordered magnetic field structure, which increases the polarization signal, and the warm neutral medium, or WNM, has a more disordered magnetic field structure, leading to less coherent polarization signal. But the problem is, we can theorize about what the structure is, but it's hard to, I guess, prove that with only two-dimensional observations. And so what I wanted to do is think about how we can use simulations to test this picture of the magnetic field in the ISM. And so the simulations we used were run by Drummond Fielding and his collaborators. And so these are 2048 cubed simulations of a turbulent magnetic field. And the neat thing about these simulations is they have kind of self-consistent cooling that allows for natural formation of a multi-phase neutral medium. So then we can ask how the magnetic field behaves in like the CNM, the UNM, the unstable neutral medium, and the WNM, the warm neutral medium. And here's just the obligatory pretty picture showing the total hydrogen column density on the left, the mass fraction of the cold neutral medium in the middle, and the polarization fraction on the right. And so the first thing we did was like, okay, we have these synthetic observables. Do we see the same correlation? And the short answer is yes, we do. So these are similar reproductions of that first plot I showed you from Minji's paper, showing the Spearman correlation between the polarization fraction and the mass fractions of the cold, unstable, and warm neutral media. And the different panels just show sight lines for different numbers of cold clouds intersected along the line of sight. So for essentially all of these cases, there exists some region of total hydrogen column density where the polarization fraction is positively correlated with the mass fraction of the cold neutral medium. Great, except for maybe down here where if you have more than 20 distinct cold clouds along your line of sight, then your signal's starting to get scrambled, which fair enough. All right, so we reproduced qualitatively this observed scaling relation, but does that mean that this cartoon picture is true? Well, we don't know yet, or not just from reproducing that. So having reproduced it, we started looking into the more simulation-oriented ways of analyzing like the cold gas and magnetic field properties. So first, this is looking at how the magnetic field tends to align with gas clouds of different temperatures. So what we did here is we looked and picked an axis as a line of sight and measured the length, the one-dimensional length of different clouds along that line of sight. And the y-axis shows the average angle between the average magnetic field vector in that cloud and that line of sight. So a value of 0 would be a magnetic field that is perfectly aligned, in the direction of the line of sight. And so what we would expect if the magnetic field were aligned with the cloud is that the longer the cloud is along your line of sight, which means you're more likely actually looking at that cloud like along, its long axis, then we would expect the magnetic field to also be, the angle between the magnetic field and the line of sight to be smaller, which is what we see for the CNM and the UNM, and not so much in the WNM. So this is hinting at that, yes, kind of our expectations of the magnetic field being more aligned with CNM structures seems to be holding true here. Because these are simulations, we can also more directly probe, is that my 2-minute time? No. We can more directly probe the actual contribution of the cold and warm gas to the polarization fraction that we calculate. And so here, this is the distribution of polarization fractions for the cold and warm gas as a function of the number of cold gas clouds that you intersect. And so you see, until you really reach 20-something cold clouds along your line of sight, the cold component is really contributing more to the polarization fraction. And lastly, we kind of looked more directly at the disorder in the magnetic field. So here, we looked at individual cold clouds. And so for each, or individual clouds of different temperatures, and for each cloud, calculated an average magnetic field vector. And then for the size of the cloud, we calculated this is the kind of middle 50th percentile of the magnetic field, kind of the spread in magnetic field vector. And so what you see is for cold clouds, especially as you get higher in mass, you have less disorder in the magnetic field orientation than you have in the warm cloud. So I actually think that this does support the picture where the magnetic field is more ordered in cool gas and more relatively disordered in the warm neutral medium. But with an important caveat is that this image is not to scale. So actually, maybe I'll go back one here. So here, this picture kind of very, clearly shows that less disorder in the cold, more disorder in the warm. But if you were to plot the same image with cloud length on the x-axis, you get the inverse picture. And this is because cold the CNM has characteristically smaller length scales than the WNM. So if you're thinking about it in terms of physical space, which as simulators we often do, you can convince yourself that the magnetic field is more tangled in the cold medium. But it really, I think the magnetic field is more aligned with the CNM, but the CNM changes in, it changes in direction more frequently in space-time or in space than the WNM. But in observations, what we observe is actually the mass column density. So if you're thinking about it in mass space, then the CNM has a much more ordered magnetic field than the WNM. And so moving forward, one of the things we're going to do is think about making some bespoke simulations of a turbulent magnetic field that's a little bit more like the high galactic latitude sky, because the simulations we looked at here were much more kind of dominated by the CNM and much more turbulent than the high galactic sky that the observations were made of. And then hopefully that can lead us to some predictions for the polarization of the magnetic field with gas phase. All right, so thank you for your time. I'd love to take your questions.
Questions? There.
What's the physical reason for cold neutral media being more ordered? Because I expect for cold neutral media, the turbulent dynamo is less efficient. Magnetic field amplification is also less efficient. So plus 1 beta should be larger than 1. I expect it to be less ordered. So I wonder what's the physical reason.
Okay, part of my mental picture is that, like, as you have gas collapse, you're affecting like the magnetic field with it. Like we do see that the magnetic field like traces these wispy like CNM structures. I think I guess more ordered. When I say more ordered, I mean it is more aligned with the actual structure of the CNM itself. It's not that in cool gas the magnetic field is like more relaxed, or like it is a very turbulent, tangled magnetic field, but so is the CNM structure, and they just trace each other. And that's kind of what I mean by more ordered.
In the back.
Hey, can you go back to your motivation plot and maybe even just your analysis plot where you see this peak in the, that one.
The analysis plot, sure, yeah.
Yeah, you can do this one or the other plot. I mean, do you understand why there are very specific densities where it peaks, and it seems like this alignment is stronger?
Yeah, so maybe, I'm trying to think if it was more useful to use the observed data or the, so I think at very low column densities, you have the magnetic field or the polarization fraction also scales with the total hydrogen column density. And then at very high column densities, which is primarily driven by the cold neutral medium, once you get past a certain threshold, you just have way too much, way too many different clouds along your line of sight that they're kind of mixing the signal. So you're not getting a coherent kind of relationship between the polarization fraction and the amount of CNM you see.
Okay, Rafael.
Okay, Irina, thank you very much for the nice talk. I want to ask about the definition of the cold neutral medium, because there are several definitions in the literature, right? And the exact borders are not definite, right?
Yeah.
So, did you check how the definition of the cold neutral medium might affect this analysis, and is there any implication for the comparison of the observations?
We did check. So the temperature distribution in the simulation, it's like kind of bimodal.
Yeah.
So as long as you pick something by eye or by motivation reasonable, so where you're not cutting out a large fraction of what should be, that cold medium, it all kind of looks the same with, some minor quantitative differences.
Yeah.
Okay, we have to move on. Let's thank Irina again. You have to offer.
And he's turned off.
I just said that. Give a warning.
I'll give you 2 minutes before 12. Yeah, perfect.
Mm-hmm. Hello? Can you hear me? Yes, great. Can you go back?
Spoiled your talk, sir.
Oh, it's okay, it's okay.
All right.
Can I use this one? Oh. Okay.
Okay, next we have Rafael.
It's not projecting.
Why? This is above my pay grade. I don't know what.
What application is your talk in? Is it
PDF.
It's in PDF.
Okay, so this is Keynote that it's sharing to the screen right now.
Oh, I see.
I've
Probably we need to
opened
go, view, full screen mode if you go. And then share this window.
And you should be able to just click on that window and then minimize it.
Click on which one?
This one?
The presentation is in its
Oh.
own window that's like on that screen.
Let's see. Minimize this. And now put this over there.
Sure. As you wish.
As you wish.
Go to the front screen. Leadership skills spike the leadership skills.
You should be able to just switch the
Yes.
the desktop.
Oh, I can't try.
If you, yes, exactly.
Is it like a 2-finger swipe or something to go to the other desktop? It's got a swipe.
Yes, great.
There you go.
Okay. All right. Sorry.
Great.
Slideshow's gonna auto move it forward on him, so I would escape from there and actually do enter full screen instead.
Oh.
What Andy was dealing with this morning. It's the same thing you did a moment ago. View and then.
I think it looks like we're going to need a new section on the application form.
Okay, great.
Okay. Rafael, take it away.
Thank you. Okay, hello everyone. I'm Rafael Skalidis and I'm a fellow at Caltech. So Irina has very nicely set the stage for this talk. I'm going to talk also about magnetic fields, polarization, and more specifically, I will focus on, I will present our new results on how we can constrain the magnetic field strength in the ISM. So in terms of the energy budget, the magnetic field is roughly as important player as anything else, and so we cannot ignore it. It's very challenging to constrain the magnetic field strength. We can usually do that through the Zeeman effect, but all these observations require long integration times and are noisy. And for this reason, the community has traditionally relied on indirect methods, which employ dust polarization. And dust polarization comes from the outcome of the interaction between spherical dust grains and magnetic fields. And this cartoon here describes this effect. So spherical asymmetric dust grains align their short axis with the magnetic field, and thus the starlight passes through the dusty cloud. It gets preferentially absorbed along the long axis of the grains. And so we observe the starlight being polarized along the magnetic field axis. And complementary to this, the same grains emit thermal emission, which is also polarized, but perpendicular to the magnetic field lines. In any case, with both effects, either in optical or far infrared and sub-millimeter wavelengths, trace the orientation of the magnetic field in the plane of the sky, but not the strength of the field. And in order to get some information about the strength of the field, we need to be a little bit more creative. And the idea goes back to the 50s, when independently Davis and Chandrasekhar and Fermi developed a method to constrain the magnetic field strength from dust polarization maps. For convenience, I will refer to this method as DCF. And the idea is the following. Consider a cloud that is permeated by a uniform magnetic field. Then, if we obtain polarization measurements, the polarization angle map will look uniform too. And now consider that we add perturbations to the magnetic field morphology. Then the observed polarization angle map will become dispersed. And the larger the perturbations compared to the mean field component, the larger the dispersion in the polarization angle map. So this is the main idea. So mathematically, the DCF method can be shown by this mathematical expression here, which relates the magnetic field strength with key quantities: the gas volume density, the gas velocity, the density, the gas velocity, and the dispersion in the polarization angles. But the problem is that this method, when it was tested in numerical simulations, it was found to systematically overestimate the magnetic field strength. And for this reason, several modifications have been proposed. But the problem is still there, because the method assumes that all these perturbations are due to incompressible waves. But the ISM is highly compressible. So we relaxed this approximation, derived a new equation which uses the same observables, but has a different scaling, which you can see over there. So we tested, we can express this difference in the scaling in terms of the Alfvénic Mach number, which is a metric of the magnetization of the turbulence. And here you can see the prediction of the DCF method, and this is the prediction of the new method. So we tested this difference in the scaling in synthetic data that we produced from MHD numerical simulations. And the figure here shows the results. So the figure shows the dispersion of the polarization angles as a function of the Alfvénic Mach number. The black dots correspond to the synthetic data, and the magenta line shows the linear scaling of the old method, and the blue line shows the new scaling of the new method. And you can see that the old method fails to fit the data, while with the new method we obtain a very nice and great consistency with the synthetic data. So the scaling is correct, but the actual question is, does the new method improve the estimates that the magnetic field strength estimates? And to answer to that question, we applied both methods to the synthetic data. And I will start with idealized turbulence in a box simulation, which resemble the dynamics of diffuse ISM clouds, and then we'll proceed with more complicated collapsing clouds. So in the diffuse clouds, we applied both methods and calculated the relative difference between the estimated value and the actual value. And this relative difference, or relative error, is denoted as epsilon here. Please note that in this, when we applied the DCF method, we included the previous corrections in this test. And the figure here shows the relative errors of the DCF method in the vertical axis, and these are the relative errors of the new method. The colored points correspond to our results for simulations with different Alfvénic Mach numbers as indicated in the legend here. And as you can see, the points in the vertical axis can go up to 3,000%, which means that the DCF method overestimates the true magnetic field strength by an order of magnitude, and even more in some cases. While in the horizontal axis, all the points remain below the 20% limit, 50% limit, which means that with a new method, we can constrain the true magnetic field strength with an accuracy that is better than a factor of 2 with a new method. Okay. Now let's move to self-gravitating clouds, more complicated situations where we have self-gravity, we have chemistry, and we also test different projection angles. So the top row here shows the column density map of the collapsing cloud. So this is the column density, and from right to left, the inclination angle of the mean magnetic field decreases. So the mean magnetic field here is in the plane of the sky, while here it's pointing towards the observer. And these red segments correspond to the synthetic polarization measurements. In the bottom row, you can see the polarization, the corresponding polarization angle distributions. And you can see that when the magnetic field is in the plane of the sky, the distribution is bimodal. And this bimodality is induced by the collapse of the cloud because due to the flux freezing, as the cloud collapses, it drags the field lines and creates this hourglass morphology, which is consistent with the observations. But as the inclination angle decreases, the two modes merge, and we end up having a unimodal distribution. So this is the effect of self-gravity in the polarization data, and we observe similar effects in the synthetic emission line data, which are required for the estimation of the magnetic field strength. So this figure shows synthetic CO emission line data, which were created using a non-LTE radiative transfer code. So this shows the antenna temperature as a function of the gas velocity. And again, we can see these two peaks in the distributions which change with the inclination angle. Okay, so these are the effects of self-gravity and the inclination angle in the observables. And which we need to minimize, which we need to account for in order to get reliable estimates of the magnetic field strength. And we have tested all possible ways to do that exist in the literature, and they are summarized here, I mean the most basic ones. And I have highlighted the most efficient methods for accounting for these self-gravity and projection effects. So in order to reliably constrain this, the intrinsic spread in the polarization angles, we found that fitting multiple Gaussians works very well. We managed to constrain the gas velocities through the second moment maps of the synthetic emission line data, and to constrain the gas volume density, we have used multiple emission line data and fitted them with publicly available radiative transfer codes like RADEX. So this is a three-step formula that we have developed and any observer can use in order to account for all these effects in the estimation of the magnetic field strength. So using this three-step formula, we can apply both methods and test their accuracy, their performance. So I would like to note that during these tests, we split into two groups. One group was in charge of creating the synthetic data and providing the ground truth parameters. The other group was in charge of blindly applying the methods without prior knowledge on the true value. Okay, so the results are summarized here. These are busy plots, so let me guide you through them. The distributions correspond to the volume-weighted and the CO-weighted magnetic field strength distributions. These are the actual distributions. And the various, the vertical lines correspond to different statistical quantities of these distributions, like the mean, median, and the mode. This cyan, this magenta point, corresponds to the estimates derived with the old method, the DCF method. And the sign point corresponds to the estimates that we derive with the new method. We considered as the ground truth the median of the CO-weighted distribution, which is shown with this blue dashed-dotted line. And you can see that the old method deviates more than 3 sigma away from the ground truth value when the magnetic field is in the plane of the sky, and as the inclination angle decreases, the magenta point goes closer to the ground truth value. So overall, the previous method performs well only when the magnetic field is inclined with respect to the long axis, to the sideline axis, while the new method is shown with this sign point, is consistent with the ground truth value within 1 sigma for every case that we studied. Since I'm running out of time, I will skip this part and I will conclude. So we have developed a new method for the estimation of the magnetic field strength that uses polarization data, and we have also developed a 3-step formula that any observer could use in order to achieve high precision estimates. Thank you very much.
Questions for Raphael? Yeah.
So for your formula, I wonder whether you need to incorporate the dependence on inclination angle, because I see in your simulation,
yes,
the inclination angle you change and the
yeah, no, that's true. The inclination angle actually affects this the dispersion, the polarization angles. But note that this method is essentially sensitive to the plane of the sky component of the magnetic field. So this is already incorporated in delta theta.
Additional questions? Yes.
Cool talk. I guess,
Thank you.
I'm curious about how this is robust against kind of what we heard about in the last talk about maybe mixing, different parts of the ISM on the site. Like, is this something that we can really just apply to nearby systems or things that are like, really isolated?
Yes. Okay. This is definitely something that we can apply nearby systems, and it is designed for this kind of systems. You cannot apply to. I don't mean that this works for extragalactic. For other galaxies, right? So this is small scale stuff like cloud scales, and it's not affected by the different phases because, as Irina mentioned, the dominant, the CNM, the cold neutral medium, has the maximum contribution in the polarization signal. So we are tracing the magnetic field in the CNM, and that's why all this approach can work only for the CNM. There are other ways that you can develop in order to trace the magnetic field in the other phases of the ISM. Yeah.
We have time for more questions. If not, I have a question. From an observational side,
yes,
what would you like to see? What would be ideal, like in the future, next 5 years, with space or ground-based telescopes?
Okay, that was the last part of the talk, which I skipped because I was running out of time. So what I would like to see is, in brief, we want to test these methods on sky, right? Not with simulation data. And in order to do that, we have found some regions where we know that we can detect the patterns of MHD waves, and using the dispersion relation of MHD waves, we can get independent ways to constrain the magnetic field strength, and we can cross-calibrate all these approaches on sky in some specific areas of the interstellar medium.
Fantastic.
Yeah.
Okay.
Thank you.
Let's thank Raphael again. going to try to do it. This side. You want this one?
Yeah, this one.
Okay. We're going to drag this.
Okay.
Over here. And where's the buzz? Down here, right? This one?
No. Slideshow. Oh, no.
Is it that one? No.
Okay, it works.
Good. Okay. Last talk of the session, we have Yuhu talking about 3D magnetic fields in the ICM.
So hello everyone, I'm going to also talk about the magnetic field, but here I'm going to move a little bit to larger scales at megaparsec, kiloparsec, intercluster media instead of small scale interstellar media. So first let me tell you why do we need to care about the magnetic field on the very, very large scales. So we have a lot of cosmological simulations and our cosmological surveys shows the distribution of galaxies is not uniform in our universe. Actually, they concentrated in a cosmic web code. But actually, cosmic web is not just a concentration of galaxy distributions. It also consists of gas density, like here that form cosmological simulation, and here that very dense noise where a galaxy cluster is emitting X-ray emissions. And also we have radio emissions from realistic cosmic synchrotron radiations. And if we have radio radiation, we also have magnetic field. Therefore, if we wanted to fully understand the large-scale cosmological structures, we need also the information of gas distribution, radio emission, and also magnetic field. Then we can complete the picture like for the large-scale structures. And the typical way to trace magnetic field is synchrotron polarization in the gas cluster. And the polarized synchrotron emission is perpendicular to the magnetic field. So if we rotate the polarization vector by 90 degrees, we get the orientation of plane sky magnetic field. And here is one example of detection of magnetic field orientation in one of the gas cluster. And the synchrotron radiation, because it's propagating from the radiation source to the telescope, in the propagation is also affected by the Faraday rotation, which is determined by the thermal electron and also plane alongside the magnetic field. So if we detect the Faraday rotation, it also gives us the strength alongside magnetic field. So the polarization study has already largely advanced our understanding of gas clusters or magnetic field in gas clusters. But I have to say the limitation because the polarization signal is suffering the depolarization effect. Here that's the polarization reaction P, which is signal to noise ratio. It's affected by the turbulent depolarization effect. So if we have very strong turbulence, and the polarization fraction becomes smaller, and also Faraday rotation depolarization effect also correlated to turbulence. So because of this very significant depolarization effect, up to now, the detection of radio polarization signals only achieved in the radio release region, which is outskirts of the gas cluster, and here that's the center of gas cluster. Because in the outskirts, we have shock waves can compress the magnetic field, also compress the gas. So it's highly polarized, the magnetic is more ordered. But in the central regions of gas cluster, the radial halo is located. There's not any detection of polarization signal because it's very turbulent and the depolarization effect is very significant. And it's very challenging to achieve any polarization detection measurement for the radial halo region. That's the first limitation, and also have to see the traditional polarization method can only give us a 2D magnetic field, either the plane sky magnetic field or the line of sight magnetic strength. But we all know that the magnetic field is a three-dimensional vector. So we need not just the plane sky angle, we also need to know the inclination angle of the magnetic field and also the total strength. Then we can get a full picture of magnetic field instead of just one component. So in this talk, I'd like to address this question: is how can we get the 3D magnetic field in gas cluster, especially the radial halo? So the first problem we need to solve is to get rid of the depolarizing effect. Of course, the solution is very simple. If we have depolarizing effect, then we don't use the polarization, and we are looking at another observations, like here for just synchrotron intensity map, which is not polarized, or X-ray intensity map, which is also not polarized. They are not suffering the depolarizing effect. So possibly we can use those two observations to get the magnetic strength, magnetic information. And the second question is, how can we use like the untraditional unpolarized synchrotron intensity or the X-ray intensity observations to get the 3D magnetic information? So let me show you also an example of what the data look like. Here, that's one example of the gas cluster measured by radial observation. Here it's just unpolarized synchrotron radiation map. And we see they have the structure of the synchrotron radiation intensity structure is very filamentary, and we can highlight several examples here, 3 examples here. And the structures, we can characterize them with very 3 fundamental morphological features. The plane sky elongation direction, here for example, here is elongating along this direction, here is elongating along this direction. And also we can characterize these structures by aspect ratio that's between the ratio between the major axis over the minor axis. And also we see the structures are curved, they are not straight. And here this one is straight and this one is curved. So those are first 3 fundamental morphological features we can get from the radial observation. And my goal is to find whether there's any correlation between just morphological features of the radial structures and the 3D magnetic field, information in plane sky angle, inclination angle, or magnetic strength. So let's see firstly what's up, because we want to find the correlation, we need to understand what's the properties of the intracluster medium. So firstly, it's very highly turbulent for the intracluster medium. The turbulent velocity detected by the X-ray spectroscopy shows it's larger than 100 km per second, and magnetic field is relatively weak. For the part rotation measurement is around 1 microgauss. So because the magnetic field is very weak, and also the intracluster medium is very turbulent, so we need to separate the regime, the intracluster medium into 2 regimes. One is at a very large scale, where we have essentially hydrodynamic turbulence. Because the turbulent kinetic energy is larger than magnetic energy, magnetic field is not important. And if we go to smaller scale, because turbulence is cascading, so eventually at small scales, the turbulent energy becomes smaller than the magnetic energy. So magnetic energy is more important, and the magnetic field in smaller scales could be more dominant. So at the large scale, we have hydrodynamic turbulence, and in this regime, because magnetic field is dynamically weak, therefore weak magnetic field is passively advected by turbulent flows or non-turbulent flow. Here is one of the numerical simulation of turbulent box, and here that's a synthetic radial observation map, and the black segment is magnetic field. And what we see is magnetic field always aligned with those radial structures, synchrotron intensity structures. And this simulation has very good magnetic field. Magnetic field energy is much smaller than the turbulent kinetic energy. And you may say, okay, this is just a turbulence simulation. It's too simplified, and the really unrealistic. The gas cluster is more complicated. But actually, this alignment between magnetic field and the radial structure is also observed in the cluster simulation. And also, as I showed in the beginning, is in the cosmological simulation. Here that's the radial structures, and here that's magnetic field. Magnetic field always align with the radial structure. That's what happens at a large scale. So if we go to smaller scale, as I mentioned, into another regime, magnetic field becomes stronger. Yes, we see some change for the structures, because magnetic field is much stronger, and it has more important role in regulating the structure. But even if we see in a simulation, even if we have stronger magnetic field, the structures, the radial structures, is still aligned with the magnetic field regardless of the magnetic field is strong, or whether magnetic is strong or magnetic is weak. So up here, maybe you already have the answer of how can we trace the plane sky angle just based on the morphology, because we know the elongation direction of the structure, and the structure is always aligned with magnetic field. So if we know the elongation direction of the structure, then we know the magnetic field direction. And here, that's the one of the polarization detection from the Meerkat telescope, and we say that's as we expected. Here, the magnetic field lines well aligned, well agree with the elongation direction of such structure. So so in observation, of course, we don't want to use the polarization signal. We want to get rid of the polarization, get rid of the depolarizing effect. So we need to find a way to detect such elongation direction. So we propose to use the intensity gradient method, because we have the properties is elongating the elongation direction. Elongation means the parallel scale or major axis is much larger than the minor axis. So if you calculate the intensity gradient of such structure, you find the intensity gradient is dominated by its perpendicular component. Therefore, the intensity gradient of synchrotron intensity or X-ray intensity are perpendicular to the magnetic field. And we tested this method using numerical simulation with very weak magnetic field. And we see the intensity gradient method actually can recover the magnetic field very well. That's in simulation. And in observation, we also want to test it. And so we compare the magnetic field traced by the synchrotron intensity gradient with the polarization measurement for the RxJ1314 gas cluster. And for this cluster, we have some partial detection of polarization at radio relief region, but we don't have any detection for the radio head region because of the depolarization effect. And what we see is in the radio relief region, so the two measurements has very good wavelength, but the advantage for the synchrotron intensity gradient is we don't need to consider the depolarization effect. Therefore, we can complete the magnetic field maps in the or magnetic field geometry in the radio head region. So here, that's beautiful kind of image from the JWST telescope. And previously, we only know the distribution of galaxy, and we also know the distribution of thermal gas by the blue shadow area from Chandra X-ray emission. But now, with the synchrotron intensity gradient, we can also know the distribution of non-thermal gas and the structural magnetic field, and also the dynamics of gas flow. Okay, so here, okay, that's the second answer to the second question. Actually, the morphological features in the radio and X-ray data has information on magnetic field, and we can use the intensity gradient method to extract the magnetic field information. But here, what we achieved is just the plain sky 2D magnetic field. What we want is 3D magnetic field. So let's see what we are missing. Actually, we also have two parameters not used: aspect ratio and the curvature. So we know the structures are elongating along the magnetic field, but this elongation is actually 3D, not a 2D. So what we observed is projected elongation. And the aspect ratio, therefore, is affected by the projection effect, which is defined by the inclination angle. And of course, this aspect ratio is also affected by strength. Stronger magnetic field has stronger compression. And that's for the aspect ratio. And also, that's the same for the curvature. Well, curvature is also related to the magnetic strength. If we have strong magnetic field, we can expect a more straight magnetic lines. And if the magnetic field is weak, the magnetic field line is more curved. So we have the two parameters, aspect ratio, curvature, and that correlated with inclination angle, magnetic strength, is enough for us to solve the correlation and solve for the 3D magnetic field. And if you want more information, actually you have more morphological parameters, which I just ignore here because those three are very fundamental. So to find the correlation analytically is very difficult. So I propose to use machine learning tool to extract the correlation between the three morphological features and the 3D magnetic field. And here is just one example of the convolutional neural network we proposed to extract the features, morphological feature in radio observation. And our input data is just synthetic radio simulation, and we can give prediction for the 3D magnetic field. And we have tried different machine learning architectures. Each of them has different advantage, and this machine learning approach is not limited to the large-scale intraclass media, but also the diffuse ISM and also the star-forming regions. Here is the last slide, and here that's a comparison for the observation test of the machine learning method. Here that's polarization, traditional polarization method measurement, and here that's the machine learning prediction. We see they have a good agreement, but actually if we use machine learning, we can do much better, do much more than just the traditional polarization method. We can get the plane sky angle, we can get the inclination angle, and also magnetic strength. So that's the summary slide. Thank you so much.
Rafael.
So these are distant objects, right? So when you make all these observations, you're targeting very distant objects. So I was wondering how the foreground contamination or interference with other systems might contaminate the observations.
It could be. So when we are doing, like for this example, I chose just a nearby diffuse radiation region. If you have foreground, actually you need to consider in numerical simulation and train the machine with the foreground correction. So here for this region is particularly selected without considering for foreground, and it matches our numerical simulation conditions. But if you wanted to do something more like star forming region foreground, you need to do more another numerical simulation.
Yeah.
I was really fascinated by this recreation of the Planck polarization prediction. Have you thought about this in conjunction with thinking about foregrounds for B-mode polarization of the CMB?
Yes, actually, it's published in my another work. I didn't talk about it. Yes, I think it's a very powerful way to trace the foreground polarization. We can use the H1 data, and use same method to train the simulation, train the machine with simulations, and maybe also constrain have some observational constraints from polarization or Zeeman splitting, and combine them together. Maybe we can get a better template or foreground polarization.
You have an idea of how your error bars from this measurement track into like a sigma R?
Obviously, it's difficult because we don't have ground truth in observation. We only know what happens in numerical simulation. So for machine learning, I cannot see how big the error is. So the only comparison is plane sky magnetic field orientation. Maybe, I don't know about how to constrain the error bar.
Okay, we need to move on. Let's thank you again.
All right, and we have the changeover of the chairs. Hello, everyone. I'm going to be driving us through the probes of the young universe. I believe Nick is online. I see you there. Sorry, Yui, come on. This is our first remote presenter of the day in a brand new chair, so let's see how this goes. Oh my God. All right, he's a champion. Brilliant.
Awesome.
Great. So, hang on. Is that it? It's all good? We're all set up? Okay, I've literally had zero training, so it would have been really cool if you could have, I don't know, showed me something. How do I get to that?
There's somebody in the booth in the back, and he said, "Hang on a minute."
Oh.
Yes, yeah.
Sorry. Thank you. We're hanging on.
I have to go to then get to that screen.
Oh, okay. I don't need to be in the microphone. Oh, but something's up. Okay. Okay. I'm sorry to call on you like that. Thank you.
Like this.
Nick, can you hear us for the second?
Can you hear me?
Brilliant. Just while we're getting things set up, I'm going to give you a 2-minute warning. Would you like me to somehow wave at you through a camera, or would you like me to just interject and say 2 minutes?
I have a timer here, so I can do that. Or
right.
if you'd like to just interject. Yeah, I'll keep it as close to 12 minutes as possible. So yeah, thank you though.
All right. I trust you. If you've got a timer on hand, that's even better.
Yeah.
We're just, I don't know how much you can see, but we're just getting things sorted on our end.
Yeah, no worries.
Should have prepared a short stand-up routine, so I'm sorry.
Nice not to change the settings. Sorry, guys. Our map guy's coming, guys. Sorry about this. You know to extend more. All right, our guy's coming in here just a sec. Since they changed this, I don't know. We got a guy coming in here just a second.
Okay.
Something about sharing on Zoom.
It's somebody's changed this display settings from mirror to extended, and so we can't get to some of the things that we need to.
Okay.
See, it used to be right in there, but it's been changed to where it goes now. I want that change back. See, it won't go to that. Perfect. This is coming out of the speaker's time, right? So I have 3 minutes to talk.
Correct. Nick, I hope you're condensing your talk as we speak.
Yeah. Very good.
Scan it. It's not even reading it. Oh, looks like it's disconnected. See, it's not even there. He's sharing again. Why is that?
Hey, Nick, you share the screen again.
You might have to read this. Why is that not sharing?
Are you still sharing?
Because what happens, he'll share it, and we plug that back in.
Difficult.
Why don't we just do it like that for now?
Yeah, because I think it's.
Can he just run like this for now?
Yeah, is he up?
Oh yeah, but he's not sure.
Yeah, if it's his thing, we can. Why is that not popping up now?
Hey, Nick, just share your screen and we'll continue like this. You have to share one more time, sorry.
That's so weird. I don't understand why it's not doing it now.
Make it.
Did I do it? Yeah. Display settings.
His expertise.
I don't. That's so weird.
take a fake.
All right, that's his screen.
There's nothing to do.
All right, let me try something real quick. Okay, I got that up now. Okay. So, but we want to share his presentation from here?
If he can share his
Or
screen, he can control
Okay,
it.
this is good now. Nick, can you share one more time, please?
Hopefully the last time.
Yes, hopefully last time.
Thank you so much. Is it going to be annoying to transition out of Zoom mode into regular mode, or is that?
No, we should be
Okay,
good now.
beautiful.
Yeah, for some reason it got
Have the
funky, so yeah, so he should be good. Sorry.
Okay. I think we're good to go now, Nick. I think we can see your screen. We can see your slides. So
Awesome.
thank you for your patience, everyone. Appreciate it very much. Off to a good start. So first up, kicking us off, we have Nick Kern talking about some multi-wavelength cosmology at Cosmic Dawn. So go ahead.
Awesome. Thank you. And I have timer here, so should be all set. Okay. Well, thank you. Thank you, Haley. Thank you to the NHFP leads. Thank you to the NHFP SOC and the entire staff for making this all happen. So you're right. I'll be talking today about some of my work at the intersection of intensity mapping, cosmic dawn, and high redshift astrophysics. So I'm the first Cosmic Dawn talk, I believe. So I'll give a very brief overview for those of you who maybe need a refresher. And trying to understand why is Cosmic Dawn so exciting right now. So, right, Cosmic Dawn marks the birth of the first stars and galaxies in the universe. There's a lot that we don't understand. And what you're seeing here is a visualization of how we think this may have happened. In blue, you're seeing the ionization fronts generated by the first sources as they inject.
Nick, I'm so sorry to interrupt your flow. It's an excellent flow, but I think we're seeing like the keynote file and not the slides themselves. Can you like maybe if you like play the presentation?
It was playing, but let me.
Oh, okay.
It was playing. Is this better?
We can see you like manipulating it, yeah, but I think so. You did press play. We were just seeing the title slide.
How about now?
Yeah. We have issues again.
This is the wrong window.
Are you sharing the wrong window? Like when you press play, it's like mirroring the screen, perhaps?
Nope. But let me just do this. Let me share the entire screen. I was sharing just the. Let me just share the full screen and see what.
Yeah, that's usually a good.
Is this
fix.
better?
Yes. Okay. Love it. Brilliant. Okay. Carry on.
Okay. Let me carry on here. Okay. Right. Okay. So can you all see this graphic here?
Yes.
Yes.
Yes. Okay. So right. So so what you're seeing here is these ionization fronts eat into the neutral hydrogen shown in red. This is in the intergalactic medium, left over from recombination. And this process occurred over some time, and what we're left with at the end is the galaxy field, and all the neutral hydrogen being effectively reionized. And this is what we're seeing directly with JWST and HST for the first time at high redshift. And what's important about this is that it's setting the stage for the emergence of modern stellar and galaxy populations, and as we see today. However, like I mentioned, there is a lot about this process that we really don't understand. We don't know when these first stars and compact objects formed. We don't know what their IMFs were or their radiative properties. And even though we're beginning to learn this in a little more detail, we really don't know which sources drove this reionization process. We don't know in detail the topology of the EOR throughout this process. We don't know the temperature and the ionization history as a function of redshift. Why are these things important? These things are important because they pin our models of structure formation at high redshift. Right? If we seek to understand a comprehensive picture of luminous structure formation, it all kind of starts at high redshift here. So we really would like to know these things in detail. And of course, as I'm sure that we will hear throughout the week, we have learned a lot from recent JWST observations. And as I'm sure we'll hear, there are some new puzzles as well, one of which is the apparent overproduction of galaxies above redshift 10. So what I'm showing you here is the evolution of the hydrogen neutral fraction as a function of redshift, which we know at low redshift, at redshift 6 and above, is pinned to be ending at around redshift 6. We don't have a good understanding of what's happening above redshift 8. And if you take some of these JWST observations at face value, what it tells us is that there's too many ionizing photons being produced at high redshift. Okay, so this is kind of the photon budget crisis, so to speak. And there are ways to resolve this tension by fiddling with some of the astrophysics, lowering escape fractions, or making it a little more bursty, or perhaps changing the relationship between the faint end and the bright end. But I think the point I'm trying to make here is that for everything that we've understood with JWST, there's a lot more that we don't understand. And in particular, what we need are complementary observations to really pin down what's going on at very high redshifts. And it turns out that 21 centimeter cosmology, i.e. mapping the neutral hydrogen that exists via its spin flip transition, its 21 centimeter transition, is a very complementary probe. So it's sensitive to the total photon budget coming out of these galaxies, both the UV photons and the X-rays. This is kind of driving the point home between the complementarity here. So this is a now somewhat outdated forecast of constraints on the UV luminosity function. This is the number of galaxies we observe in a given brightness bin. And we've known that JWST will not be able to probe all the way down at this very faint end slope and resolve this kind of turning point here at the faint end. We think that a large fraction, if not the majority of the photons responsible for ionizing the EOR actually come from these faint end. So when you combine measurements, say, of restframe UV and 21 centimeter here in this turquoise, this dark green here, you can see much tighter constraints on what's happening at the faint end slope. Furthermore, we have very few measurements of what's happening in X-rays. So this is a very rough graphic showing you the difference between the simulated 21 centimeter signal with X-rays on top and without X-rays on bottom. So the point here is that the signal is very sensitive to how X-rays are produced and how they propagate to the IGM. And with these radio data sets, we hope to learn something about the first compact objects and how they're heating the gas. Okay, so where do we stand today? I'm going to give a very rough overview of the state of the field right now. And this is the best upper limits on the 21 centimeter power spectrum at the EOR and cosmic dawn prior to 2022. So we don't have direct detections yet, but what you can see is that over the past 5 to 10 years, we've made steady progress in pushing down in this parameter space. We have about a couple orders of magnitude of ways to go. And one of the telescopes that we hope will get us there is this now completed telescope called the Hydrogen Epoch of Reionization Array, or HERA, which is what I spent a lot of my PhD on. This is a telescope that we built in the Karoo Desert of South Africa, and it actually shares a site with the SKA MID, which you can see right in the top right there. But this is our telescope, HERA. It's a compact interferometer with roughly 350 individual dishes. Its compact size gives us access to the large angular modes in the sky that we want to map out. And it's going to be using the 21 centimeter line to probe structure from redshift 5 all the way up to roughly 27. So it's going to allow us to probe really deep into cosmic dawn and test some of these very high redshift astrophysical models. And I'll be talking a little bit about data that we took and analyzed with only a small fraction of this array in the bottom left-hand corner here. So with only a fraction of its total sensitivity. So, and the limits that we put out a couple of years ago, shown in here in orange, and subsequent limits that we put out in red. We've used HERA data to set the most sensitive constraints in the power spectrum. And again, this is really with only a small fraction of HERA sensitivity that we're now observing with. And what's interesting is, so we have about an order in 1.5 orders of magnitude left to go here, but with these very sensitive upper limits, we can begin to rule out some interesting astrophysical models that to date have not really been disfavored. And in particular, the models that I'll be talking about are these so-called inefficient heating models. So we know that the gas temperature in the IGM cools adiabatically at high redshift. That's this orange line coming down. At some point, the first compact objects form and they inject X-rays into the IGM and heat the gas. And that drives the gas temperature to high temperatures. but there are variations of the standard model that would suggest that perhaps structure formation is delayed, or that the X-ray heating is somehow inefficient. It either doesn't escape the ISM or is inefficient at actually heating the IgM. And so you can have kinetic gas temperatures in the IgM that remain very cold all the way down to redshifts 10 and below. And it turns out that existing data does not rule out these models. So if you look at UV luminosity functions, quasar absorption spectra, and the CMB optical depth together in gray, you can see there are models of the average IgM temperature at redshift 8 that are only a few Kelvin. This is adiabatically cold. It's only with the inclusion of Hera's recent upper limits that we can say for the first time at 95% confidence that the IgM must have been heated above redshift 8. So this is quite interesting, and you can turn this around and say, well, if the IgM must have been heated, there must have been something heating it, and so we can set for the first time indirect constraints on the X-ray efficiency of these first X-ray sources. And if you assume that it's coming from a high redshift population of high mass X-ray binaries, what's really interesting is that we can say for the first time that there's a preference for a lower metallicity population of high mass X-ray binaries that is entirely expected at high redshift because we expect the universe to be lower metallicity, but to date, we have no direct evidence for. So this is really highlighting our ability to learn about these high redshift X-ray sources in novel ways for the first time. Okay, so that, as I mentioned, is only a fraction of Hera's sensitivity. We're now taking data with substantially more sensitivity, and we've already analyzed a small data set from that new data. So there are new upper limits that should be coming out in the next couple of weeks here, and I'm highlighting here upper limits that now span redshift 5 all the way up to 25. These upper limits at the redshift that we've already measured are not more sensitive than our previous limits, in part because we're only working with a very small amount of data. This was really a proof of concept to demonstrate our high redshift data reduction pipeline. So you can see for the first time, this is the first time that we'll be setting limits above redshift 16 with Hera, and we're now going to be deploying this pipeline on over a year's worth of data. So the really exciting stuff will be coming very soon. Okay, so in the last couple of minutes, I'll give a little bit of an overview of how we're going to be going from upper limits to direct detections, because this is where a lot of the really critical science can be found. And I've done some work recently to try to develop some models to enable this paradigm shift. So in addition to things like end-to-end pipeline validation and statistical null tests, one thing that we don't quite have in the field is a way to fully understand how our uncertainty in the foregrounds and instrumental systematics impact our ability to reconstruct the 21 centimeter signal. And I'll just give a brief kind of highlight of this framework that I've developed over the past couple of years, developing the first end-to-end Bayesian-formed model for 21 centimeter intensity mapping, which is going to allow us to more robustly understand how uncertainties in our instrumental systematics actually impact our 21 centimeter power spectrum measurements. And so it's just a kind of a proof of concept. This is the first time that on a mock signal, we've been able to actually explore this full joint posterior distribution. What you're seeing here is uncertainty in the EOR maps corresponding to covariant uncertainty in both the foregrounds and, in this case, the beam response. So this is going to allow us to set much more robust error bars and build confidence in our initial detections. The other really exciting avenue coming down the road here is other ways to try to beat systematics, which are one of the limiting factors. And in particular, there's going to be kind of a deluge of future multi-wavelength data sets on Cosmic Dawn in the next couple of years, which will allow us to cross-correlate them against the 21 centimeter field. What's really interesting about the cross-correlation is that it's much more robust to the systematics found in any given probe. So let's assume that we have two data sets, Y1 and Y2. They both are sensitive to some signal, S1 and S2, which perhaps has some underlying shared information content. Maybe it's somehow related to the dark matter field. They have some systematics, X1 and X2, which are uncorrelated, and they have noise. If we were to take the autocorrelation of each one, we pick up terms like X1 squared and X2 squared, which create a bias. But when we cross-correlate them, we pick up terms like X1 and X2, which average down to 0. And so the cross-correlation technique is a very promising way to act as a kind of smoking gun signature of initial detections in the 21 centimeter signal. And in the last minute here, I'll just say that there's a number of really exciting opportunities for doing this, in particular from future alignment alpha emitter catalogs from Roman. And this has been forecasted, and what we can find is that there's a smoking gun anti-correlation between the 21 centimeter signal and the Lyman alpha emitter signal, in part because Lyman alpha emitters tend to occupy the overdense regions where we observe no 21 centimeter signal. And in the last slide here, this is a forecast shown for the ability to detect this signal, even by throwing out all the data in the 21 centimeter data set that's contaminated. We can still make a roughly 10 sigma detection with HERA and possibly a 50 sigma detection with the future SKA telescope. So yeah, lots of exciting avenues in the future for leveraging this multi-wavelength data sets. And with that, I think I'm out of time. So happy to take questions.
Thanks so much, Nick. Maybe we can take a quick question while I think Christian is next and come and get mic'd up. All right, well, maybe Nick, you can tell us about the kind of timeline to this robust detection that you're telling us about. That's so exciting. Like you said, kind of the methods that you would do to go about that, but when do you kind of expect this to happen?
Yeah, so in terms of the cross correlation, there are data sets right now. So for example, Subaru has Lyman alpha emitter catalogs. Oh, I think it disappeared, but I think you can still hear me. But it's really about survey over. Yeah, it's about survey overlap. So we don't have really good survey overlap between existing high sensitivity radio measurements and then say Lyman alpha emitter catalogs or other intensity maps. That will change in the next couple of years, especially with Roman, where we're going to get its high latitude survey will overlap really neatly with both the SKA and HERA. So that's in a couple of years, but we expect to have initial detections even sooner than that with some of these more advanced Bayesian forward modeling frameworks applied to HERA data. So it overlaps pretty well with our ability to make initial detections in the auto power spectrum and then in the cross correlation roughly on a 3-year timeline.
3 years. All right, I'll hold you to that. Awesome. Thanks so much, Nick. We'll give you a big round of applause again. Oh.
Yep.
Yeah, so. All right.
Let's cross fingers, but I think it's okay.
Brilliant. All right, excellent. So next up to the stage, we have Christian, who's going to be telling us about some exciting DESI results. I'll give you a 2-minute warning like this. Otherwise, take it away.
Thank you so much, Kelly. Yeah, so I have plenty of slides, so let me just start saying that my name is Christian, and today I chose to talk to you about the latest results we got from DESI early this year, okay? So then first, let me give you a quick context about what DESI is, but tomorrow you will also have the talk by Andre. But basically, as the name says, DESI is dark energy spectroscopic instrument, and as the name already implies, basically DESI is an instrument which measures the redshift from distant galaxies by using a spectroscopy, right? So then this instrument here is located at the Kick Peak Mountain in Arizona, and what DESI does very good compared to the precursory surveys that they used to do this kind of analysis is that DESI can measure a lot of redshifts, more redshifts at the same time. So basically what the telescope does is like it focuses at some patch of the sky, then the light comes and hits the primary mirror here of 3.8 meters of diameter, and then the light just bounces here through this system of optical lenses that help to focus the light until arriving to the focal surface, where then you have an army of 5,000 robotic fibers. So basically each of these fibers here, is basically 0.1 millimeters in aperture. It's like the size of the thickness of a hair. And this is very nice because each of these robots, they can actually move to locate the galaxies in the sky. So for example, each robot have like 2 degrees of freedom of motion, right? So one movement is like if I move my shoulder, and the other is like if I move my arm. So with these 2 types of motions, basically they can cover a patrol radius, we call it, of 6 millimeters in radius. And later on, of course, once all this has to go down like 200 kilometers of wire here to analyze the spectra down here. So the results that I'm going to show you today are from the data release 2. So basically data release 2 means 3 years of observations. So to put you into perspective, redshift measures the redshift of galaxies from redshift 0.1 until 2.1. Basically, we have different objects given the target selection program. But for this data release, we got around 14 million galaxies. So compared to the previous data release, which was only 1 year of data, at the time we used to have almost 6 million galaxies. So now we have 14 million. And this is very nice because if we go even farther in redshift, we can use Lyman alpha emitters to reconstruct the large-scale structure of the universe. So then another very nice thing that we have in this data release is that as we collect more and more data, our sample is more uniform. So basically, we say that the completeness has improved from going to DR1 to DR2 analysis. And this, as you can imagine, is simpler because it is easier to model a uniform footprint compared to something that has holes in it, right? So then the idea is that DESI will provide us with a 3D map of the universe while covering around 1/3 of the sky fraction, right? But what do we want to measure? It's basically a signal that was originated in the early universe. So back in the time of recombination, basically the universe was a primordial plasma in which, for example, particles like us, like the baryons, they feel the gravitational they try to gravitationally collapse into overdensities dominated by dark matter. However, the baryon also interact with the photons, which exert radiation pressure. So then this competition of two forces induce an oscillation in the baryons in the plasma that propagates at sound waves around 50%, 57% the speed of light. So then there were several oscillation modes. However, there is one mode that is of particular interest to us, which is the longest a sound wave could have traveled from the time of the Big Bang till the time this decoupling happens. And the decoupling, I mean, once the photons detach from this picture, and then this acoustic wave here just basically stalls. This is very important because later on, as the universe evolves and you have the galaxy clustering history later on, this basically is just leaving an imprint that, in principle, you can measure later on in the large-scale structure of the universe. So tomorrow, Andre will talk to you about the measurements. So I will just say, like, if you have a 3D map of the universe, you can calculate the correlation function. And basically, you can isolate and detect the BO signal at different redshift bins. And this BO signal will manifest as a bump in the correlation function. If you do that, it's very nice because then you can get conclusions on cosmology. So for example, if you imagine the subtended angle by a BO shell, you can basically expand that, and you will find out that you can get information on how much matter we have in the universe, omega m, and also this weird product over here, which is h naught times RD, the size of this BO scale. But this is very nice because then in DESI, we're measuring this BO feature at different effective redshifts. And then basically by doing that, we can combine the measurements, and then we can get just tightest constraints. But this is very nice because it's basically a signal that got originated in the early universe around 400,000 years after the Big Bang. You are measuring its imprints like billions of years later. So it is very cool, actually. However, what I want to talk right now, because it's the part that I was mostly involved and also part of the paper writing, is the cosmical results. So then in this first figure here on the left, what I'm showing you are the results from DESI DR2. So then you can see two things. So one is like DESI DR2 is consistent to the results we got in DR1, but also is consistent with the previous results that other precursory surveys like SDSS found in the past. However, as we get more data, we are just getting tighter constraints. So this is an improvement of around 40% with respect to DESI DR1. However, the interesting things in the conclusions they came once you start analyzing how the DESI results look with respect to other cosmical probes that are available over there. So then, for example, DESI by itself prefer a low value of omega k, picking around 0.285. And then if you look at the CMB primary isotropies measured by Planck, they will prefer a slightly higher value of omega m. And then if you look at supernovas, they all consistently prefer even a higher value of omega m, right? So then this helps us to start talking about in the domain of the cosmical tensions. So then in this plot, what I'm showing is a comparison of the BO results with respect to the Planck CMB results. So one thing that we were noticing in DESI is like as we got more and more data, basically our constraints shrink, but then the discrepancy between DESI and CMB is slightly increased. So this is basically just a mild 2.3 sigma, but then we are reaching basically a regime in which all these discrepancies ended up mattering later on in the conclusions. So for example, there was something very funny that happened after we released the results. So there was actually a simultaneous press release from the Atacama Cosmology Telescope. So this is another collaboration that basically measures CMB anisotropies, but it's a ground-based experiment, so they are very good at resolving the small-scale anisotropies. So something that we were able to do was to update our analysis in light of the new data from ACT, and we found that just comparing DESI with ACT alone, the discrepancy we did was above 3 sigma, and then depending on how you combine DESI and ACT and Planck, then the discrepancy can oscillate around a mild 2 sigma. However, there was also another press release later on by another thing called South Pole Telescope, which also they measured CMB anisotropies, but they focus more on polarization measurements. This was very nice because what they did is like they provided a consolidated CMB data set. I would like to think of it like that. Because basically, if you look at the paper, what they did is like they combined the data from Planck, which is a space satellite, with ACT and SPT, which are ground-based experiments. Sorry. So if you do that, basically what they found is like currently the tension between DESI and CMB stays at 2.8 sigma, right? So then right now people are going to start talking about all these discrepancies in cosmology, but a very nice thing to see on what's going on in the results is like you just compare the model versus the data. So in these first two plots over here, what I'm plotting is what we're plotting is the BO measurements, so the isotropic BO measurements, the anisotropic BO measurements, and in the last panel, we are showing the measurements of the distant modulus from type 1a supernova, choosing DS Wi-Fi to highlight what's going on. So then this horizontal line over here is just the Planck CMB best fit lambda CDN model that we take as a reference. And then what we want to see is like how well we can fit the data with the standard model. So then if we combine DESI with CMB, what we will see is like lambda CDN can actually very decently fit the BO measurements. However, it will fail to fit the supernova measurements. If we, on the other hand, we take the best fit lambda CDN model from DS, it will actually fairly good fit the supernova data because it will even be able to fit this low redshift data point, but at the same time, it will fail to describe the BO measurements. So then what we try to do is to look for extensions. So the simplest one is just to go to a WCDN model, which is a constant varying equation of a state of dark energy. If you do that, it doesn't work because this model ends up resembling a lambda CDN model. So then you have to go to the next extension. And if you do that, this is basically allowing for a time varying equation of a state of dark energy. And what we could see is like this can actually fit the data, and even the model is flexible enough to fit the low redshift data. So then this helps us to conclude that currently we are seeing some preference for this WWA depending on how we combine the data sets that can range in around 3 sigma all the way to over 4 sigma. And we were able to verify this with other model-independent approaches like Gaussian processes. On the other hand, something that I would like to say is like there is currently also the problem with the neutrino masses when we try to constrain it with cosmology. So if you just take the constraints as such, the data sets as such, and you say, okay, there is no systematics with my data, basically, if you remove the effect of the prior, then the constraints on the parameters like the neutrino mass are just getting nonsense values. So then extensions like this can actually help to alleviate a little bit those sorts of problems. So then let me just conclude with this slide, which is we need to wait for more data, but I think I'm very hopeful that we will be able to have a better picture of what's going on in the next year. So for example, there are several options right now, so 6 thematics in the biodata. My biased opinion is that I do not expect so, given the reasons that I put here. There could be also potential systematics in the supernova data, but fortunately, we will have soon other reanalysis. Systematics in the biodata, in the CMB data, this could be actually a potential a real problem over here, which is mismeasuring the optical depth reionization parameter, but I think we should be able to figure out by indirect measurements what is going on with this parameter. So finally, I will say like we need more data, and fortunately, we will have more data releases in the next years to come, and then we will verify if we are actually going in the road towards a phi sigma detection and the model is compelling to us, or basically we'll find out that there is some systematics, and this road was just an illusion. So thank you so much. Yeah.
Thanks, Christian. Super cool stuff. Just going to kick off the questions for us. It's going to be me. Sick. All right. So you said like you need more data, but like what do you actually think is going on here? But it's not systematic. So what is it?
I don't think it's systematics in the biodata. Right now, from what I have observed, I think if there is, well, but this is my biased view, okay? Don't tell to the supernova people community, but I think the good thing is like, for example, from these alternatives I put here, things like systematic in the CMB data by mismeasuring the optical depth, I think that's something that can actually revert the things. The only thing is like you need to then somehow disregard the supernovas in absence of systematic. So the issue is like it's a game between three players over here. Another thing that is very interesting, and that could actually push the results very strongly, because dark energy is a late-time phenomena, and for example, in the case of BO, we do the best as we can, but if we keep going to smaller and smaller redshifts, we don't have enough effective volume to actually conclude something by ourselves. But the supernova people can actually do it, right? So then, I don't know how official it is, but there will be some reanalysis in the supernova community that will shed us some light. So I think it might either be some sort of systematics. The CMB optical depth issue, I think, is a serious candidate, but otherwise, we just need to find a compelling model, because something that I didn't mention here is like these indications are getting stronger, but then there are some issues if we want to just theoretically interpret the constraints as such, right? But not an easy question, so maybe we can discuss more. But,
yeah, for sure.
Yeah.
Time for one more question?
Go ahead.
One more, yeah.
Kind of more like self-interactive dark matter.
Yeah, so that one self-interaction you say?
Dark matter, self-interactive dark matter.
Yeah, I mean, I haven't checked much about that one. The one that I have checked is, for example, things like interacting dark matter with dark energy, because then something that could help there is like if you can see there is some sort of apparent crossing. So if you have models like that, those can actually produce effectively a crossing like that in the equation of a state. The issue is like if you go to those kind of models, what you need to verify is like, okay, you are able to fit this geometric data, but then you don't screw the growth rate of a structure. So then that's something we need to keep in mind in the first. But we are going to do a lot of analysis, but yeah, need to wait. Yeah.
All right, let's all thank Christian again.
So you have your own?
Works. Can you guys hear me?
All right, and wrapping it up for this session, we have Jessica. Take it away.
Hi, I'm Jessica Zabrowski. I'm finishing up my fellowship at University of Chicago, going to transition into a faculty position at University of Chicago next fall. And today I'm going to be talking with you guys about cosmology with line-intensive imaging.
So this is history of the universe. I'm sure many of you have seen this cosmic history diagram before. Big thing on the left, now on the right. And here I've marked out where we get some of the information about our universe's history from. And the thing that I think is really striking to me is that we get it mostly from the endpoints. So we know a lot about the earliest light of our universe in cosmic microwave background, the experiments like SBT and BICEP for the Science Observatory. And then we know a lot about our universe framing on closer as to how it is today with galaxy surveys, things like LSD, DESI, as we just heard about. But these are really just the two endpoints, and as everyone who's taken the here knows, with 2 points you can draw a line, but with 3 you can see if it's evolving as the line goes on. And so this is why during my postdoc I thought I was really enchanted with this new technique called line intensity mapping. So this uses emission from atomic and molecular lines from galaxies, like CO, C2, hydrogen, as talked about with 1 centimeter earlier. And this maps the 3D galaxy distribution, all of the integrated emission, as it evolves over time. So the data product is a 3D data cube. This seems awesome, obviously, but there's a catch. So the first one is that you need many, many detectors in the sky to measure cosmology. And the second catch is kind of a double-edged sword. So this is a very new field. So no cosmological constraints have been measured yet, which is, sort of an open landscape, but also really exciting as a young person to be getting into. So what is this measurement? What you measure is low resolution intensity maps of atomic or molecular spectral lines at multiple frequencies. That's the data. But what this traces, as you can see, like here's your low resolution intensity map. What this traces, though, is the large scale structure in the underlying galaxy population, which of course traces the dark matter distribution and web as it evolves over time as the spectral line redshifts. This is really complementary with the CMB. So the CMB is obviously called like surface of last scattering because it's a surface. And with line intensity mapping, you're getting a map like the CMB, but at multiple redshifts, so it's a cube. So while the CMB gives you one cosmological epoch, LIM gives you many. The other thing about LIM is kind of cool is you get a much different number of modes. When you're chasing after these large-scale linear modes, we are running into sort of statistical uncertainty problems because there's no more modes to count. Something like line intensity mapping, you can get access to all of these more large-scale linear modes. This is also really complementary because it breaks generously for the CMB. So it's like a different measurement of tau that you're talking about, getting away from that here. But the cool thing is that because CMB is also sort of this field that you do cosmological analysis on, you can use a lot of the same intuition for cosmology analysis that you do with the CMB with line intensity mapping. This is also really complementary with optical galaxy surveys. So this is a fundamentally different tracer, cold gas versus optical light. You also have this potential for higher redshift because it's not multiple, it's inexpensive with the Dustin intervening universe. You can go almost into redshift 10 of many lines of minutes and fast as many lines like CO2. And you can go back and forth almost to the dark ages with things like 21 centimeters. And the big difference between these here is that with intensity mapping, light intensity mapping, you get all of the integrated emission. You're not like pointing at individual galaxies. It's a survey experiment. But of course, it's going to be so powerful in cross correlation. These are going to be really, really synergistic together going forward. The third thing is that it's worth it doing in more than one line. So in this image at the top, you see like the galaxy distribution on the left, and what you would see in a 21 centimeter experiment versus a CO experiment for the exact same galaxy distribution. So each atomic species reflects different properties of the host galaxies. So for example, with many galaxies that ionizes the IgM, which leaves a hole in the 21 centimeter map. But with many galaxies, there's tons of star formation that produce metals, so you get a bright spot in the CM map. So in this way, sort of interleave together and give you a full picture of what the universe is doing. And also, you get different instrumentation systematics. Systematics is always a big deal to come here. So being able to measure 2 different lines, 2 different types of frequency bands, different instrumentation is going to be super powerful. And then, of course, the cross correlation here will be very rich. But really, all this is what I want to emphasize, that light intensity mapping is this really a new window into the universe, spanning all the way back to the cosmos. This is something this is a lot of people are taking my hopes and dreams for the field of light intensity mapping. So this can potentially constrain cosmological parameters against current CMB and galaxy survey constraints. So on the y-axis here is basically the error bar of Planck relative to the error bar of LIM. And in the legend, you can see some of our favorite cosmological parameters. So we can constrain things like inflation and the history of the very early universe, some of the neutrino masses, new light-relevant particles, dark energy. And as you're moving towards the right of the plot, you're starting to see this very, very significant increase in sensitivity relative to Planck. This x-axis is spectrometer hours, which is just a statement that if you want a more sensitive instrument, you can either integrate or load or put more detectors in the sky. So number of spectrometers or number of hours is something direct. And to get to this cosmological promise, we really need to get to the right side of this plot. Right now we're about here, the far left side of the plot. This case is the So what is the state of the art right now? It's something like time. This is an image of the time experiment. So time is a spectrometer that has its R100 spectrometer with about 60 central channels. And this takes up a volume of about 700 cubic centimeters. And what's gotten me so interested in line intensity mapping right now specifically is that there's this new technology called on-chip spectrometers, which are this scalable technology that can get you to the right-hand side of the plot. So on the right here, you have SPT Slim, which is also an R100 65 spectral channel spectrometer, but this is on the footprint of 0.5 cubic centimeters. And that is a huge, huge improvement in terms of scalability. And this is the basic idea behind this experiment, SPT Slim. So the South Pole Telescope Cherenkov line intensity mapper. And the idea is to demonstrate this line intensity measurement using these on-chip millimeter wave spectrometers, which are the scalable, unique technological advantage in the field. So we deployed a high-density, 9-pixel dual polarization focal plane. This is sensitive at the top for 120 to 180 gigahertz, which is sensitive to the CO lines between enriched 0.5 and 2, so the CO 32, 21, and 43 transitions. And we deployed last November to the South Pole Telescope. So how this works is that the South Pole Telescope is this 10-meter telescope at Amundsen Scott South Pole Station. And many of you guys might know the SPT from the usual set of CMP experiments that are housed in the SPT, as you've shown in a plot in the last station, actually. So if you can imagine like the big dish of the SPT off to the right of the screen here, how this usually works is light comes in from the big dish, like a 10-meter dish, hits our secondary mirror, tertiary mirror, and it goes down into the SPT 3G cryostat. And last summer, they let us take our line intensity mapping experiment, SPT Slim, and actually put in a different, like sort of re-imaging optics to get hit off the main beam using the big resolution of the big dish, but allowed us to put our own experiment there with SPT Slim without disrupting the actual SPT 3G experiment. So zooming in a little bit closer onto the instrument itself, light comes in from the top into our focal plane. That's where the detectors are. This is a cryogenic experiment. So it's cooled down to 4 Kelvin with a pulse tube cooler here, and down to 150 millikelvin with an adiabatic tube ionization refrigerator. So radiation is emitted by these conical feed horns on the top, and coupled to these on-chip spectrometer filter banks I was talking to you about by these planar OMTs. So here you can see our ortho-mode transducers. That's our antenna. Light travels down to these filter banks. This is like a zoom in here, and then it gets channelized off into all these different frequencies, which then correspond to these different redshifts, which builds up the cube that I was talking about in terms of data volume. And what's been really exciting is that this is renderings. But as of last year, this is actually real. So last fall, we took our focal plane down to the South Pole, going from Chicago to McMurdo, Antarctica to the South Pole. So we can carry our fragile equipment in, like the focal plane. The rest of the cargo went to the cargo hold in these giant crates. And here we took the whole team to the South Pole last year. We got our cargo on December 3rd, 2024. And then we started building the experiment. So here you can see the rendering of the focal plane at the top and the AVR at the bottom. On the right is the real simple picture. From there, myself and my colleague Matt put in a ton of coaxial cables. And so you can see on the bottom the full instrument package of the SPT Slim cryostat with the deployment team. A few people in that picture because they're rotating it at different points of the season. From there, you take this whole instrument package and insert it into your cryostat. So to keep something cold, you have to have a bunch of different cryogenic shells. You go out from 300 Kelvin room temperature, 50 Kelvin to 4 Kelvin, and then all the way down to 1,000 Kelvin right at the focal plane. Here you can see a picture we all took the first night we got the cryos on the pump and started cooling down. After we characterized it, it was all the way on the ground. We lifted it up into the South Pole Telescope, so we actually lifted it through, like in the negative 20-degree weather in Antarctica. It was a very cold day, and then dropped it into the boom over there in the telescope. And then you can kind of imagine how this all lines up with the rendering I showed you before. So now you have the secondary and tertiary like imaging optics here, which then go down into the telescope. We got first light with RCW38 on January 15th, which is a H2 region. You can see when we see it on our pixels. So it's really exciting for us to actually be able to build hundreds of spectrometers and see something in the sky. And we took a bunch of other characterization data last year. One visual highlight that I'm actually really excited about, despite being less than exotic astrophysical object, which is the moon. It has this really nice characteristic of being a high signal to noise polarized black body. And if you're trying to have a almost always polarized black body is actually great for this. This is the start of objects counters of FBT SLIM. So we had our first deployment this year. We're hoping next year to take down a deployment of more sensitive detectors and actually do like a much deeper cosmological survey. But the question is, of course, like how do we get from here, from like the first imaging seen in the sky, to these orders of magnitude improvement that you need to do cosmology? So right now, right, we're here, like 10 to the 5 spectrometer hours. Where we really want to be is this 2 orders of magnitude more up, because that's where you're starting to become competitive with galaxy surveys. So in my mind, there's 2 limiting factors. So the first is detector count for focal point area. If you want more detectors on the sky, you're going to need to build a bigger telescope, which is obviously extremely expensive, or get more clever about the way you pack it in. So right now, our SCT focal plane has one major flaw, which is that, well, flaw is just another word, okay, feature. That the only part that you see light is actually at the center. It's these pixels, these are like our antenna. So it's as if we're losing all of that light, because it doesn't actually need to be co-plated with the detectors. So we've been developing methods where you can rotate these actually vertically. This is a concept we're calling the vertical integrated spectrometer that myself and Jeff McMahon are working on. And you can pack in a bunch more detectors into the same exact area at the same exact price tag. The second limiting factor is actually material science thing. It's dielectric loss. So when light comes in and hits your antenna and goes on the feed line, gets channeled off into all these different redshifts, this is the ideal case, but actually you have this exponential decay from losses in the materials itself. So I've been working on this, I believe it's a project called LANCE, which is using materials developed for quantum transduction to try to make next-generation cosmology devices. So we've been with our colleagues like Ali at TU Delft using their really cool dielectrics to try to fabricate cosmology. There's a few text there. This is saying that we made some of our core samples earlier this year. And after that, we test them at U Chicago. So we had these whole processing cryogenic setups and analysis pipelines to see these resonators and see how much better these lattices will do for sensitivity going forward. And our real next step is to have another big nanofabrication campaign, moving away from these like little test vectors and tiny boxes into actual detector architectures that will enable like these future cosmology projects. And this is all sort of working towards what I use like moving for latency, which is just that it becomes like the next CMP. So I hope that we'll have this like wide survey in the Atacama Desert concerning dark energy equation of state, Hubble constant inflation, like a deep survey at the South Pole between matter power spectrum, galaxy bias, and galaxy formation and evolution. And even hopefully one day like a lit space mission to gain the sensitivity to these lines that you can't access from the ground and getting away from atmospheric contamination. So I'll leave you my summary slide. I think the future is really great for this field. We're at the point where we're getting these first experiments on the sky, taking real data, and developing the future. And hopefully it'll keep progressing in sensitivity so that I'll be able to present to you guys someday with these like cosmological straight from life. Thank you.
Thanks, Jessica. Questions? Yeah.
This is fascinating. Congratulations. So I'm showing my spectrometer inside me, and I'm looking at your R100 and the analogy you made with the surface of last scattering over CMB.
Yes.
It seems to me, correct me if I'm wrong, we're looking at them at this point as we were looking at Kobe back in the day.
Not even.
No, in terms of resolution, right? So I'm thinking about, would you think if there's a gain to go from R100 to R200 or 500 in terms of spectral resolution at some point in the future?
Yeah, so like right now, like again, I can't emphasize how new this field is in terms of other than 21 centimeter lines. No one's even made a detection of the CO power spectrum, much less like really characterized in a tomographic way. People are like collapsing bins or doing really big bins. So most of the analyses that we're doing are trying to look at changes. Like the sensitivity is such that we're artificially binning our redshifts, even bigger redshift bins to try to gain sensitivity. So with this generation of experiments, no, but in the future, definitely yes. And pushing to higher R, like there are people building R300 spectrometers, for example, now for LIM. But as far as that, how fine a resolution you actually get a trade-off, it's of course a trade-off between sensitivity and one map versus multiple maps. You can of course create like synthetic larger bins and stuff like that. But yeah, so like, the current state, no, but in the future, potentially yes.
Final question. Go ahead.
Amber. Thanks for an interesting talk. I'm curious about how does your the SPT thing differs from the traditional single dish antennas, for example, like SMA?
Yeah, so SPT is just a single dish radio antenna. It's just a 10-meter big dish with some like refocusing optics, which are just mostly to like actually really collimate the beam. So it's an off-axis Gregorian telescope, if that's the answer to the question that you're asking. But yes, it is just like one big 10-meter dish that can do between millimeter to sub-millimeter resolution with the roughness of the mirror.
So can you like do the survey with, let's say, GCMT, for example? Is that possible?
Yeah, so a lot of people, the one that most people like think of in terms of like, can you do this survey with like X telescope is ALMA, because people are like, oh, this is covering the same frequency bands, this is whatever. And it actually helps to like have a bigger field of view because you're only going after the integrated emission. You're not going after the really fine resolution stuff. You don't, and it's like if you're taking a tiny, tiny beam, it takes like longer to go across the sky. So by actually making a bigger, slightly blurrier beam, you do better. So we're using the SPT because we're friends with the people who run the SPT. And what you really only need is like a 4-meter telescope to get most of the sensitivity to the main cosmological signals that you need. So 10 meters is a little bit of overkill even for what we need, but it's a, you know, I'm not saying no to telescope time on a telescope, right?
All right, let's thank Jessica again. Difficulties. Are we having a micro coffee break or are we coming back a little late? Does anyone have authority here? If it's me, I'll say something. But
come back by, but we cut break. We have a half an hour coffee break, right?
Yeah, but we're running 23 minutes late, so correct. Yes.
You guys are good.
Well, we had some technical difficulties. That's the only reason. Yeah.
Why don't we have a 15-minute coffee break?
Excellent. So see you guys back here at 10 past. Brilliant.
Esto es de Bogotá. Sí, sí. Y en la nacional conociste, supongo, a tu profe, Giovanni Pinzón.
Yeah, she's in so I was, but I'm going to go down there. Yeah, no, well, it's yeah, no, I could, yeah. We have wonderful. We have someone she knows really well. Comes in every day, almost
Abandoned.
I was hot. Yeah, it's right. There's another group there. There's most of them is a little further away.
All right, Kemi, hey, we can see the slides okay. Can you just unmute your mic real quick? Let us know we can hear you.
What you're working
that's what we kind of talked
obviously not.
Sorry, I think it was muted for a sec.
Yeah, good. So, okay, Kyle, we can hear you okay. I think we did a test. You want to just go ahead and share yours real quick? And we'll just begin.
Yeah. Is the connection okay? I'm in kind of a rural area right now.
It's a little blocky, but as long as you're not changing WebEx too fast, we should still see it. So, who was it? Kemming, was it you that just shared, or was it Kyle that just shared? I didn't get a chance to see which slides. Okay.
Can you hear me?
So you're good. We can see your slides, we can see you, and we can hear you. So that's 1 out of 3 or 4.
So if I have a PDF preview, is the only option just to share that window?
You can share the screen or the window. So you have 2 choices when you go to share.
Uh-huh.
You
Because
can
I
share the
remember
app
for
or the screen.
Zoom, I can put the preview on full screen and then share that entire screen. I don't see that option.
Yeah, that's on your end. But on WebEx, if you just share, whatever you share is what we'll see here. So you can share the whole screen, or you can just share the application. It might be just easier to do the share screen.
Yeah.
Can I try again?
Yes, if you would, please. We'll let you know if it looks good here. It did before. It looks perfect here. Are you okay with that?
Yeah, that's fine.
Because on our end, that looks just fine.
Right. Thanks.
Okay, sure. Kyle, you ready?
Yeah. Gary, can you let me know, like mid-talk, if the quality substantially decreases? I'm actually hotspotting from my phone because I realized just shortly before that the Wi-Fi at this place is not great.
Yeah, we'll definitely look at it. Interesting. We'll give it a shot.
Yeah. If it's rough.
Well, we have another option is that we can control the slides from here if we need to.
Okay, great.
Which you would have to help with it given button presses. If you're sharing now, it's sending 1 bit at a time, and we're only seeing blue.
Yes, for sure. I would like to hear you talk.
Oh, so I'm currently sharing.
Yes, thank you.
Thank
you.
Let's see if the content changes again, because that's us. If I do that, it'll kick him off.
So also an option.
There we go. Here we go. Okay, so we're seeing the screen, and it looks pretty good. And we can hear you.
That's what I like to hear.
Now push page down. Let's see how many minutes it lags when you change the slide. Nah, that's good. Formation of wide separation substellar companions.
Yeah, it looks like it's maybe changing, like lagging a few seconds. So I can see just a bit of this screen here. So let's see, does this?
Yeah.
Ooh, that is lagging. Okay. All right, good to know. I'll some of my dramatic timing might be a little off here.
Yeah, just change the slide 5 seconds before you start talking.
Yeah. I'll do my
that's
best.
Good. All right, that looks good. And then Jaron, are you still there? Do you want to give it a shot again just in case?
Sure, yeah, we can run through it another time.
Yeah, as long as I can just see it, we'll check it.
The Murphy's Law of WebEx is pretty real, and so we got to keep on top of it.
Well, yeah. So that last one where we had a technical issue, we kept looking for what the error was here, and it wasn't. It was on the presenter's end where there was a blue button. But there was a screen extending or mirroring issue down here as well. So that is clear as can be. Are you going to do go into presentation mode?
Yeah, this was the plan. So
There
I
you
see between me changing it here and then the photons reflecting off the projector screen going through the camera and coming back, we get about half-second delay. That's pretty good.
That's good.
Jaron, I'm jealous of your half-second delay.
Yeah, I'm all the way in the middle of the Pacific Ocean, so I thought it would be worse.
Yeah, I'm in southern France right now, so it's.
Oh, never mind. Okay, yeah, you win.
Yeah.
Hey, I was over in India in October, and it was the fastest speed connecting here that I'd had probably even than when I was in the building. I kid you not, the speed was unbelievable. Is it Ayuka in Pune? And I just checked, and I didn't even change anything. It was Euroroam, or EduRoam? Sorry, EduRoam, and it just connected automatically because I walked onto the campus, and next thing I know, everything's just working as smooth as can be. What was that? 7,000 miles? Yeah. That's not bad. And this is 60 feet, so go figure. All right, guys, it looks like you're good. Appreciate it. Thank you.
Thanks.
And then we just have this one that's here, and it's ready to go. So for those other ones, it'll be either Kevin or I, and we'll just display that up there. And
Perfect. Is this a timer for them, or I can just time it myself?
You can use the timer if you like.
Is it using it? Do we know?
Actually, I don't know that. Where is the remote?
It might be easier if you just kind of keep track. See where the remote is.
Because I also feel like
people may or may not be looking, down at that.
Okay, because the remote control is not even there.
Got frustrated?
Where to look? Well, maybe it'll get used again. Who knows?
Which deal?
Because that remote is useful. Unless you got it here. All right. Well, anyways, it looks like.
This just shows what's up here. So, and right now it's mirroring. Well, these two are always the same, but then this one, we're not doing any screen extensions, just mirroring.
And I guess Kyle's first, right?
That's a good question. I do have the schedule up here. Kyle, I don't remember if Lily and Jaron are swapped to keep all the virtual at the same, but we'll be fine even if it's not. We get a slew of emails to help correct things based on what's going on, and then sometimes I lose them in my mind of.
Thank you so much.